Okay, good morning, ladies and gentlemen. So again, as is my habit now, let me first see if you have any questions for, again, either materials from last week, anything this week. Yes?
I didn't really understand, like, when he was talking about, like, an oblique force needed for angular momentum.
So the question was about the oblique forces for angular momentum. To be honest, it's a slightly strange term. However, I'll actually first introduce what we're doing this week, and this will come up. We are discussing chapter 3 in the book today, but generally speaking, we'll be discussing Newton's laws that you may have heard about, the 3 laws of Newtonian mechanics. So in other words, we'll be talking about forces and applications of forces. In fact, I have plenty of demonstrations here. For that, I have to warn you, I'll be asking for volunteers. Like, this thing is quite comfortable. The other thing that I have to warn you about is those of you in the front rows may have to duck. Just as a fair warning. Having said that, we'll then talk about gravity as one of the fundamental forces that we all experience in everyday life, and satellite and ballistic motions, and then we'll talk about angular momentum, and that we'll do on Thursday. So perhaps that would be slightly more appropriate. So I'm changing the order of things a little bit. I'll introduce you to Newton's laws first, and then we'll talk about applications, effectively, gravity, ballistic missiles, satellite motion, and the like on Thursday. I do have to actually say, I've been called out to Washington on a short notice, so I will not be here on Thursday, but as luck would have it, Professor Bob Jacobson, who some of you may know quite well, will sub for me on Thursday. So he's great. So you can ask about angular momentum. Or a little later today. So let's see, are there any other questions related perhaps to thermal motion or anything from this week? Yes?
This question came up in the Piazza, but it's about the refrigerator.
Okay, very good. I was just going to that. Right, so to be honest, I was actually intending to drop that question, but maybe it's a good thing we didn't. So you've noticed on the homework, at least some of you may have seen this question on the homework. Homework questions are somewhat randomized. We have a set of about a dozen, and then you get a random set of 5. So there was a question about refrigerators. There are 2 questions. So some of you may have seen one, some of you may have seen another, and some of you may have seen both. So the question in the homework was, the first one is, if the refrigerator door is closed, and that's how you're supposed to run a fridge, right? Your mother tells you close the door after you get food out. What happens to the room that it's running at? And that if you get in the back of the refrigerator for some reason, if, I don't know, something fell behind, you can feel warm air typically in the back of the fridge. Fridge is an example of a thermal engine, a heat pump. Basically, there's something that moves heat from one place to another. And unlike normal engines that are designed to produce mechanical work by allowing heat transfer from a hot place to a cold place, and in the process of the transfer, mechanical energy is released that can perform real work, like by moving stuff. Refrigerators work backwards. They use mechanical work, use forces that we'll discuss today. So, I can apply a force to a thermal body and use that force over some distance, use mechanical work in order to move energy from a warm place to a cold, the other way around, from a cold place to a warm place. So in other words, refrigerators work to make cold objects colder. So, and you can perform mechanical work to remove heat from a cold place, move it to a more warm place. You always have to have two things. You have to have a temperature gradient. You have to have a cold and a hot place in order for any thermal agent to work. But you can either use the temperature gradient to perform mechanical work, or you can use mechanical work to effectively increase that temperature gradient or move heat from one place to another. So fridges will take your heat from your food and move it to the outside of the fridge. Therefore, if that heat is dumped in the room warms up, if the refrigerators work as advertised. Now, an interesting question is what happens if you actually leave the door open? One could think is that nothing should happen, in that, well, you will be moving heat from the inside of the fridge to the outside of the fridge, but the two systems are connected now, and they will mix up. And so one can think that all you're doing is basically performing useless work, as it were. You're just moving the heat from one place of the room to another place of the room. On average, the temperature should stay the same. That actually isn't quite what happens, in that in order to perform this mechanical work, you have to take some energy from the outside. You're using electricity, and the engines are not 100% efficient. You're taking the energy from the outside of the room generally, producing electricity or taking electrical energy to make the mechanical work function as the heat engine, and so that excess energy is dumped generally in the room itself in the form of increase in the temperature of the wires, or if you run the pumps that are required to run the refrigerator, pumps have friction, that deposits energy into the room as well. So even though you may set up a completely connected system, a room and the inside of the fridge are completely connected. First, they're generally not in a thermal equilibrium under that scenario, but even if they were, there's still excess energy that needs to be brought in order to make the fridge function, and therefore, the entire room is not isolated. Energy comes from the outside and is dumped ultimately in the room, temperature goes up. I got my safety equipment. Oh, James? Just a second. James? Oh. Can I also get a balloon, inflated balloon if possible? Thank you. Any other questions? Okay. So I have to apologize again for my technical difficulties with the computers. What we'll be talking today about is the everyday forces. That is what actually is needed in order to change energy states of objects, so in order to perform mechanical work. These are quantities called forces. Now, are there any, actually before I get into that, I apologize again. Last logistical point. So some of you have complained, rightly so, that some of you had difficulties setting up clickers on B-space, on B courses, rather. Some of you actually asked what kind of clickers can be used, so I've gotten a new fancy clicker plus, I think it's called. This works. Tested it. If you have an old style clicker with sort of squarish rectangular ugly buttons, that works too. If you have a newish clicker tool that looks like this but not blue, that works as well. If you have a iPhone or Android app called iClicker Go, that should work as well. All of them have a slightly different ways of registering. So all of the hardware pieces, all of the pieces like this, all of the clicker like this, in the back have an 8-character identification number. If the back of yours is scratched, pull out the battery. Under the battery there is another sticker, typically. And if worst comes to worst and you cannot find it either, come to me and we can find it electronically. OETS can do it for you. So in order to register, you need to be on B courses. Let me pull this out. There's a link in the left-hand side that says iClicker. You should click on that. And then the link will show up that says register iClicker. You should click on that. And then there's a little text field that says click registration. You should very carefully copy these 8 characters, type them in, click register, and then some magic should happen. And the magic involves, so the number of your clicker and the date of the registration would pop up under this text field, or it may already be there if you've registered your device already. And if it is registered, I will pull the registration automatically online. I've posted, let me show you this. I've posted the grades for the first 2 online quizzes on B courses, something that we did last week. If your name or your grade on B courses shows up with a score anywhere between 2 and 5, then your clicker is correctly registered. There. Okay. Let me try this again. Still purple. And technology grade. Let me. Can you try this upstairs? This is the second channel. Sometimes it works better. Could we switch to, there you go, that works better. So, registration is on the clicker registration, and then you're supposed to type in the number and it should show up in the bottom. That should all work. Then check in the gradebook. If in the gradebook your score shows up, you're all set. If in the gradebook your score does not show up, if you have a dash, that means that for last week or for today, your iClicker has not registered, send me an email. Send me an email with the snapshot of this page. And then I'll forward it to B courses and complain. There have been a few known bugs in the system, so we'll investigate. As long as you're here with the clicker and your score is registered, it will be credited to you towards the end of the semester, as long as towards the end of the semester we associate your clicker with your name. All right. So let me then start on the more interesting things. We'll talk about forces. Now, one thing, there's a reason for this cartoon. Physicists like approximations. Physics, I think I said in the beginning, physics is a very elegant science. We can analyze a very complicated problem by breaking it down into simpler pieces. We can abstract and we can generalize and apply the most fundamental law possible to a particular situation. Often it requires approximations like, being in, working with spherically symmetric nice objects, often in vacuum. And of course, you have to analyze the situation to know whether this particular approximation is applicable or not. This is an inside joke about, I think the story went that it may have been even on Big Bang Theory. The story goes is that Some physicist was called into a farm to investigate why cows don't give milk. He works for a month and then comes back and says, I have a solution, but of course it works for spherical cows in vacuum. We sometimes do that. What we'll discuss today is some of these fundamental laws, which actually are applicable to a broad range of applications. So in particular, we'll talk about forces. And last 2 weeks, we discussed the concept of energy. So forces is what lets you generate or make transformations between the two energy sources or generate energy through the concept of work. So in other words, forces, well, energy is associated with motion, and the forces is something that can generate motion. And that we know very well. So if I have a ball, in order to throw it, I need to put some muscle into it. When this ball rises, then the fall goes up, the ball goes up, stops there momentarily at the top of the trajectory, falls down. The force of gravity causes that ball to move downwards and accelerate. So, if I release the ball from rest, it's the force of gravity that causes to accelerate downwards and pick up speed as it goes and pick up kinetic energy as it goes down. Forces are different conceptually from energy. Energy is a number. Energy is like, I said in the first week, energy is like currency, dollars. It has a sign, perhaps it can be positive or negative. You can be in debt, in which case your currency balance is negative, or you may have a lot of it, in which case it's positive. But it has no direction. Forces clearly have direction. I push or pull in some particular direction. If I want to throw a ball this way, I'll have to apply a force that way, like this. If I want to make this mass on a spring move, I apply force downwards. So forces are things that look like these arrows from a quiver. They have a direction, so they point in particular direction, and they also have a magnitude. So the length of this object can be representing the strength with which I push. So we call them vectors. So this is something that has magnitude and direction. And so there are three fundamental laws, three fundamental Newton's laws that describe all of mechanics. And we can apply them to every situation imaginable. And so any complicated mechanical situation can be analyzed by successfully applying these three fundamental Newton's laws to either the whole system or to parts of the systems. And so three laws read as follows, and you have heard about them or heard of them or heard them expressed this way even in popular culture. The first one says that objects in motion tend to stay in motion. This is, I think, in the Nike commercial probably. Or objects at rest, in front of a couch, tend to stand at rest. This is otherwise known as law of inertia. This is to symbolize that if massive objects are difficult to move and require larger forces to move with the same acceleration, but conceptually, massive objects tend to remain in the state, mechanically speaking, that they are. Objects at rest, especially massive objects at rest, tend to stay there. If an object is moving, it tends to stay with the constant motion. As long as no other forces are applied to it, that can last forever. You take a boulder, set it somewhere in the middle of the countryside, it'll sit there forever, until somebody pushes on it. There was the story recently, a few days ago, that some vandals destroyed some old rock formation in Utah. Idiots. That's been sitting there for, as far as we can tell, 10,000 years. So, massive objects tend to stay in the same state forever. Second law is a little bit more mathematical, and this is probably as much math as we'll do here today. It actually describes how much force is required in order to produce motion. And we measure motion in forms of acceleration, and we'll talk about this today, is we can measure acceleration in units of gravitational acceleration, G's, that you actually also hear about. You know that if you're on a roller coaster, you can express G forces. Well, so we can express impact on you in the terms of how much force, or in the units of how much force gravity applies to you. And you experience it when you are in a roller coaster, on an airplane that's taken off, or when somebody suddenly slams on the brakes in a moving car. And then the third law is that for every action there's an equal and opposite reaction. So let me demonstrate some of these laws for you conceptually. First of all, the law of inertia describes how much a massive object resists a change in its state. In other words, how much it resists a change in speed, and we know this as acceleration. So let's see a few demonstrations of this. Every massive object likes to stay in its normal space, likes to stay at rest, unless a force is applied to it. I think I did this demonstration first in the first Tuesday classes, that this is a normal restaurant trick. If you're working in the restaurant industry as a server and some customer pisses you off, you can, or if you try to amuse your friends at a cocktail party, you can perform this trick. It usually requires silky smooth tablecloth, but if you apply a very fast sudden jerk to it, massive objects will tend to stay at rest. Right? It worked, right? Wow. Now, if you are not careful and apply a force to the object, it will start moving. It will change its mechanical state. So every massive object needs some force applied to it in order to move, for it to move. And the reason that this trick works is that the silky smooth tablecloth, if I pull it very quickly, will apply very little force for a very short period of time, and therefore not move a massive china that's sitting on the surface. There is even a better demonstration. For that, I need a volunteer. I'll need a brave volunteer. I'll be recreating the, that Apple commercial from 1984. We'll be doing that here, or something very similar to it. So I'll need a volunteer to demonstrate the law of inertia and also to demonstrate the concept of pressure. Anybody? Bueller? Come on down. Now, while you're coming down, you should think about what you did today, yesterday. Think if you've said your prayers, if you're a religious person. I also hope that before the beginning of the class, what's your name?
Daniel.
Daniel is very brave. I hope you've signed the release forms that you will not hold us responsible for any damage. I'll give you a piece of paper later, if you survive. So we have very sophisticated safety equipment. If any of you work in labs, you know that Berkeley goes now through a very sophisticated set of safety law improvements, safety rule improvements. We all have to now carry, or rather wear, lab coats at work. In the labs, we will look like guys from Real Genius. You may want to button it up if you wish. So the first thing that I will demonstrate to Daniel is the concept of pressure. We talked about pressure last time, the fact that pressure is a measure of force per unit area. Don't do anything yet. You haven't been properly trained. So I wrote this on the board, that pressure is a force per unit area. And it's the pressure that typically breaks materials, like, can puncture a piece of rubber. I have here something known as a bed of nails. This is what monks sometimes sleep on. It's actually quite comfy. Of course, nails are sharp. These are real nails. I blew the balloon to demonstrate to you that these are real nails. What do you think? Would they puncture Daniel's skin? I mean, how tough are you?
Not that tough.
We'll find out. So, if I apply all of Daniel's weight in an area of a single nail, it will probably hurt. So the key to surviving this particular demonstration is not to apply pressure, not to apply force in a small area, but spread it around. Spread all of Daniel's weight over a much larger area like this. So when you sit down, do it. Don't jump on it, obviously. That kind of might hurt. Make sure you don't rest your arms on the nails. Just lower yourself on it. Oh yeah, absolutely. You have a safety lab coat. You have nothing to worry about. So, don't put your palms on the nails. Yeah, kind of lower yourself, and it's nice and comfortable. Maybe move downwards a little bit further down. You want to lie down? I'll give you something to put your head on. All right, it's nice and comfy.
It's not bad.
How's that? It's not bad, right? You can sleep here.
Yeah, actually.
Oh yeah, right. So take a nap for a minute. I'll bring some more safety equipment. Now the second part of the demonstration. So this demonstrates that spreading the same weight, spreading the same force over a large area reduces the pressure. In fact, in this case, reduces the pressure to the point that the lab coat is not punctured, the pants are safe, and he's not bleeding yet. Now, second part requires you to wear a face shield if you want to kind of get up a little bit, so that you can put it on properly. Put this on. Tighten the back if you wish, so that the face mask stays nice in place, and lie down again. If you're good with this part of the demo, I would probably tighten the lab coat. There may be shrapnel. So the second part requires you to lie down and relax. Well, yeah, button the coat. Lie down again. So lie down. It's safe, right? So again, make sure that you don't put your weight on the nails. Be a little bit careful. Put your head down so you're nice and comfy. So we can increase his weight a little bit. Have a cement block here. Oh, it weighs less than Daniel, so that should be okay, right? Are you good to hold this? Oh yeah, kind of nice on the, probably not on any sensitive areas. We can up the ante a little more too. This cement block has a lot of inertia. It's quite massive. So if I were to strike it with a sledgehammer, what do you think would happen? What do you think, Daniel, would happen if I were to hit you with a sledgehammer?
Probably hurt.
It'll probably hurt, he thinks. So, of course, there's a reason that I have a cinder block here. Cinder block is massive. I hit it with a sledgehammer. It will try to resist moving. It's what separates sledgehammer from Daniel's sensitive organs. We'll see if they protect him, being massive and all. Are you ready? Say your prayers. Okay. Drum roll. I'll try not to miss. 3, 2, 1. Still alive?
Yeah.
Still alive. All right. Thank you, Daniel.
Yeah, thank you.
Did it hurt?
No.
Not really. So this is a demonstration, actually. This is how safety equipment, in fact, works. We'll clean it up. In fact,
Am I done now?
yes, you're done. Breathe now.
You're not going to shoot me with a...
That will be next week. The cinder block is an example of a very heavy object that resists change in motion. It has inertia. It resists being moved. So when I strike it with a sledgehammer, it doesn't move. Instead, the full impact of the sledgehammer imparts on the cinder block and it breaks apart. So instead of moving with my sledgehammer, instead letting my sledgehammer penetrate towards Daniel's bones, cinder block stays in place, and its impact crushes the block, thereby reducing the impact. This is exactly how bicycle helmets are designed to work. Bicycle helmets shatter, or supposed to crack, preventing the impact from the pavement onto your head. Very good. So this is the first Newton's law. I have to clear up the mess here, otherwise my next demonstration will put me in a bit of a jeopardy. So we'll jump into the third Newton's law that says that for every action there's an equal and opposite reaction. In other words, by action I mean forces. So if we apply a force, the concept of third law of Newton's third law says that if I apply a force in one direction onto a particular object, that object will push in the opposite direction with an equal force at me. Now, in order to demonstrate that, I also need a volunteer. I'm very interactive today. Preferably, this is much safer than the previous demo, so don't be shy. If somebody has a skateboard in class, that would work really well. If nobody has a skateboard, any volunteer would do. I'll sit you on a nice rolling chair. Anybody? Volunteers? Where? Oh yeah, come on down. Now, while you're coming down and getting comfortable in this chair, I have a few other props to demonstrate, so let me prepare. What's your name? Patrick. So yeah, Patrick, you can move this rope out of the way, make yourself comfortable. I don't think any harm will come to you. You'll find out in a sec. And I have my own props. All right. I also have safety equipment. That's one, that's the other. Well, a nice shiny lab coat that I'll put on. Try to keep my mic in place. There you go. All right, how's that? And another prop. So this is a nice piece of Canadian lumber that will be our projectile. No, not really. Of course, safety gloves. Anybody of you watch hockey? Right? Are you a hockey fan? You know about concept of dropping gloves? Right, okay. That will come later. So, you know, safety equipment. So, we'll be demonstrating the concept of push and pull, or the fact that for every action, there's an equal and opposite reaction. Could you roll in maybe a little bit closer? So, oh, maybe, yeah, get away from the stuff. So, forces can be applied either by contact. If you hold the stick, if I pull on the stick towards me, I will be pulling Daniel towards myself. What's going to happen is both of us will move. He moves towards me, I move towards him. If I push in the opposite direction, the opposite happens. Forces are applied in equal and opposite directions. The force that I'm applying on him is applied on me at the same time in the opposite direction. So I can pull and I can push. And that generates motion for both of us. The force I'm applying on Daniel is applied at me at the same time. Now, we don't have to be in contact in order to exchange these forces. You can kind of swing around. Oh yeah, this works. Forces can be applied by putting objects in contact, and the forces can be applied over distance. Here's an example of an exchange force. I can generate the force by moving the object from me towards Daniel. This object moves me, and moves him as well. Yeah, come in a little bit closer, maybe he might need to align the wheels. So again, we can generate this force, I can generate the force by passing a heavy particle, this medicine ball. That pulls me back, it pushes him back. So whatever force I'm applying by sending the object in that direction is applied to me in the opposite direction with equal force by magnitude. Demonstration of third Newton's law. Thank you, Daniel. Let me see, do I need you anymore? I think we're fine. The same exact demonstration, the fact that I can generate the force by exchanging the particles between the two objects, or by placing objects in contact, can be summarized, the same third law can be summarized in the law known as conservation of momentum. And so momentum is something that you hear about often in sports. You know, Seattle had momentum for the entire game on Sunday. Denver had none. Momentum changes 7 times a game if the game is close. It's a cliche. It's a cliche used in sports or used in describing battlefields or whatever quite often. We, being physicists, can actually assign a mathematical formula, a numerical value to this concept of momentum. Momentum is otherwise known as amount of motion. Actually, if you know German or if you know Russian, the appropriate word in German and Russian for momentum is actually translates as amount of motion, which actually is a quite apt description. What it is it's a quantity that has a direction. It points. So if I'm moving in this direction, my momentum is pointing to the left of me. If I change direction, my momentum would point in the opposite direction. Quantitatively, momentum is a product of mass times velocity. So the more massive I am, the more my momentum is. The faster I move, the larger my momentum is. So, in most physical situations, the total momentum of a system is conserved, which is very convenient when you describe collisions. So you can view that previous exchange that we had with Daniel from the point of view of conservation of momentum. If I start here with a heavy medicine ball at rest, I can throw the ball to my left. Our total momentum will be conserved. And so after I throw the ball, I will have to move to the right. The ball will move to the left. And the ratio of velocities will be such that the total sum of momentum of the ball plus momentum of me is still 0 after the collision. And the same with the table. Table moves to the left, or chair moves to the left, the ball moves to the left faster than I do, because I'm more massive. Total momentum is conserved, so more massive objects move a little bit slower, light objects move faster. The same exact concept is used for jet propulsion. Let me demonstrate that. have here a model of a jet engine. And for this, I do need safety equipment. Here's my jet engine. Rocket propulsion works exactly on the principle of momentum conservation. So the way the jets work is you have a jet engine or a nozzle that sends out gases from the nozzle with high velocity towards the back of the engine. The reactive force from that motion pushes on the rocket and propels it in the opposite direction. The total momentum of the system is conserved so that if the gases flow to the left with high velocity, the equal amount of momentum has to be given to the rocket and propel it in the opposite direction. So you can view it from the third law, Newtonian third law, that the action of the gases in this direction is counteracted by reaction onto the rocket in the opposite direction. Or we can view it from the point of momentum conservation, where the momentum given by the gases is counteracted by an equal and opposite amount of motion to the rocket in the opposite direction. Allow me to demonstrate. Safety first. I have here a carbon dioxide fire extinguisher. It can emit carbon dioxide in small amounts, not enough to cause significant global warming, to my right. If I sit on it, I'm more massive than the gases that will be emitted, but if the gases move with high velocity in this direction, I will be pushed in the opposite direction with a somewhat lower, hopefully, velocity. Let me adjust. Etc. You know, I can get to the office this way. This is a demonstration of momentum conservation of third Newton's law, where the jet action propels me in the opposite direction. So you also see concepts of momentum conservation very clearly in collisions. And of course, collisions happen in sports often. Again, on Sunday, you've probably seen very good tackles by one team, sort of lousy tackles by the other team. So here's a question that we can try to analyze. Imagine this situation. Let me start my software while you're thinking about it. But imagine the following situation. Imagine that you have a fast person, but light, fast but light person, a 100-pound, 150-pound receiver. That's roughly slightly less than my weight. Running very fast, as fast as 30 feet a second, that's 10 meters a second. That's pretty speedy. That's close to world records. That's probably not an unreasonable speed for a fit person. It's similar to this speed on skates. I can probably run at 10 meters a second on skates. A fit person can run at 30 feet a second for a very short time. So imagine a 150-pound receiver runs with the ball at 30 feet a second and then collides with a defender who's stationary. What do you think will happen? Let me do this as a clicker demonstration. Let me start my software first, though. Give me just a second. And we'll do the poll in about 10 seconds. So the answer A is receiver will bounce backwards from this heavy defender. Answer B is that both players will kind of stop and fall down. Both players can continue moving in the same direction as the guy running. Or if you've seen the last Batman movie, an explosion can happen. Okay, my software is running, so let's start the poll. I'll give you a minute. All right, about 15 more seconds. Last chance. Okay. Let's look at the results. Indeed, if you read the chapter, the correct answer, as 72% of you have indicated, is C. The total momentum in this collision will have to be conserved. So if the one person is standing still, it's like that chair with a ball. Suppose this is the defender, well, maybe a little bit heavier, and I'm running at it with high speed. We collide. After the collision, we both move in the same direction with smaller velocity, smaller speed, because now our combined mass is moving. So the total momentum is conserved, but we still keep moving in the same direction. So, your coaches tell you if you are tackling somebody, right? You have to put some force into it. You have to put some legs into the tackle. Let me actually show even better demonstrations of the same concept. I have a few videos. Let's scale this. This is actually a video of a particular collision in a football game. This is actually where this question came from. Let's observe. So here's the guy running, collides with the defender, and of course, both of them proceed to fall into the end zone. So momentum is conserved in the collision. The two objects continue moving in the same direction as long as if one is stationary and the other one is moving at high velocity, independently of what the total mass of each object is. Let's look at other examples. This is actually a YouTube video from the glory days of Cal, which are hopefully not completely behind us. This is 2007 opening day game that I watched on TV. Large forces can be generated in these collisions, and that we'll actually discuss also in a second. You'll see an impact that a collision can produce, expressed in the amount of force. Let's watch. So what will happen here is there's this poor quarterback and a star defender from Cal, Zach Follett, levels him. Both of them go in the same direction as momentum conservation requires, and even pieces fly out. Yes, in this case, the ball. So total momentum is conserved. Debris can be generated. Debris flies in the same direction. And what you should also see is how much the back of the poor fellow bends. That's clearly high impact collision. So total momentum is conserved, but the amount of force generated depends on the amount of time the collision lasts. The shorter the amount of time, the larger the force that's generated on the object would be. And these forces can be huge. So, sports like football, hockey are rather violent because of these collisions can generate very large forces that sometimes can be damaging to the human body. This is one famous example from hockey, 2007, 2000 NHL game. One of the reasons why collisions with the head are now not allowed in any major sport. This is Eric Lindros, who lost his consciousness before he fell onto the ice. He was knocked out and never played the same way. So here the poor fellow is skating at high speed, maybe another 30 feet a second or so, is met with an elbow of Scott Stevens. That elbow impacts his head directly, the head snaps back. Momentum has to be conserved. The head wants to go forward. The other guy, the defender, is skating at him. Total momentum is conserved, so the lighter object, the head, has to recoil back. The amount of acceleration experienced depends on both the amount of force applied and the duration of that impact. If duration is quick, the amount of force generated can be large. So we measure force, in fact, in more human units, we will measure acceleration. That's typically a more humanly understandable concept. Acceleration measures the rate of change of velocity. So first law of mechanics, first Newton's law says that if there are no forces applied to an object, the object keeps going forever. Massive objects resist change, inertial object resists change. But if you apply a force, you can create acceleration. I can brake. I can brake slowly by applying small force. I can brake quickly by applying large force. Acceleration is the rate of change of velocity, measures how quickly the velocity changes, either going up or going down. For example, the standard unit of acceleration on Earth is gravitational acceleration g, simply because we experience it almost every day. If you drop a ball from rest, this ball will accelerate as soon as you let it go. Accelerates with the acceleration of g in units of meters a second is about 10 meters per second squared, or about 30 feet per second squared. What it means is that every second of motion adds to the speed of this object by about 30 feet per second. So in the first second, the object falls by 30 feet. In the first second, the object will achieve a speed of 30 feet a second. In the second second, the speed will increase by another 30 to 60, then by another 30 to 90, etc., etc. So g measures the rate, constant rate of acceleration of a ball, of an object in the gravitational field. Of course, assuming that there are no other forces except for gravity, which in this particular case assumes that there's no air resistance or no other frictional forces, and we will talk about under which condition those approximations are applicable next week. Now, in this units of g, we can measure acceleration of typical objects that experience large forces. So I drive a 2001 Toyota Celica that's not made anymore, although there's a capable replacement. If I look at the spec sheet, or if I floor it, it accelerates from 0 to 60 in 6.5 seconds. Not that great, but reasonably decent. Translated to g, it's an acceleration of about 0.4. And so that you know, if you floor, if you press on the gas, you will be pushed with some force, you experience a force, you will be pushed back into your seat. You experience an increase in apparent weight, in fact. You will experience an acceleration that to you feels like a new force. And we will in fact discuss the fact that any acceleration is equivalent, according to Einstein's general theory of relativity, to gravity. If you're on a roller coaster and you're going over and over the hill and through the bottom of the roller coaster, you can experience g forces as large as about 3 g's, typically on the bottom. On the very top, you feel kind of almost weightless, right? Your stomach kind of rises up into your throat, causes you to scream. On the bottom, you feel larger forces that push you into the chair. These forces can be as large as about 3g. Roller coasters are designed to be safe, and in 99.9% of the cases they are. In fact, they're designed not to knock you out. So the largest acceleration is limited to about 3. As it turns out, if you were untrained human, you would pass out if the acceleration were to increase to 5 to 10 g's. Fighter pilots are special. They're trained to withstand high accelerations, and they can routinely experience g-forces, or accelerations of up to 10 g, 10 times larger than gravity. So at that particular situation, their weight, the way they feel themselves, their apparent weight, the way they feel, they think, or they experience their weight increase 10 times. This is a more human way to express acceleration. It's the effective increase in the body's weight. Of course, if these are accelerations applied to a body over relatively long periods of time. You will pass out if you experience acceleration of 10 g for a few seconds or so. But relatively quick jerks can create even larger accelerations. And so, in fact, the limit of concussion, if you receive a shock with the acceleration value of about 60 g or so, or maybe lower for concussion-prone athletes, you may receive something known as a concussion. Your brain will shake, you lose consciousness, and perhaps there may be even longer-term effects. So there has been relatively little research over the last hundreds of years into concussions, but it has picked up over the last decade or so. And so, in fact, most major sports now limit impacts to the head primarily because in this high-impact collision sports, one could generate accelerations of up to 100 g's for a very short period of time. And that can produce concussions that can also have long-term effects. So how much force exactly is exerted in a collision is given by the second last, the law that we haven't yet talked about, quantitative law. Second law of mechanics, second Newton's law, tells you how to compute based on the basic formulas how much force is applied to an object, or how much an object would be accelerated given its mass and given the force applied to it. So the law is simple. Force is equal to change in momentum over time. This is actually the way Newton wrote this law. The amount of force is equal to the change of momentum divided by the period of time over this change happens. So again, if I'm moving and I have some momentum, in order for me to stop quickly, I need to apply a larger force. Same momentum divided by small time equals large force. If I want to stop slowly, I apply smaller force. Smaller force means longer time. And so we can express it the other way. The more sort of conventional T-short way to express second Newton's law is F equals ma, which means force is equal to mass times acceleration. So you can measure acceleration or you can generate acceleration by applying a force divided by how massive the object is, and it will give you acceleration in the appropriate units, for example, in units of g. So here are a few numerical examples. You don't have to know how to derive them necessarily, but if you are algebraically inclined, you can. But you can look at the bottom line. For example, in that video of Zach Follett blasting the Tennessee quarterback, the amount of force was generated that's equivalent to about 1.5 g. And the way to compute it is you can compute it if you know the mass of the person, the speed with which he was moving, and roughly the amount of time the impact took. The impact actually took a relatively long time. You know, it takes a while to bend somebody's back. Took half a second, perhaps. So that amount of time, in fact, reduced the amount of force, the amount of impact, perhaps prevented the injury. I mean, that's one of the reasons human backs bend, is to, well, they have to pick objects up, but that's also a protective measure. Whenever you're jumping from some elevation, I have to be careful to perform it in my skates. Whenever you jump, you instinctively bend your knees. That increases the amount of time that it takes you to break down your fall. Increases the amount of time to reduce your momentum and stop you. If you were to jump without bending your knees, you apply a large force on your ankles. That's bad. That's a recipe for breaking your ankles. So instinctively, you increase the amount of travel, you increase the amount of time, and that reduces the force. In that video of a hockey collision, you can compute the acceleration produced was similar to about 7 Gs. That's what makes fighter pilots, well, that's what makes regular humans pass out, and the fighter pilots train for these types of acceleration. Of course, that's acceleration applied to the entire body. If the impact is applied to the head, and the head is only 10%, has the 10% of the mass of the entire body, roughly speaking, the acceleration applied to the head is 10 times larger. Since for the same amount of force, acceleration is equal to force divided by mass. So the smaller the mass of the object for a given force, the larger the amount of acceleration. If the impact is applied to the head, acceleration can be 10 times larger. 70 g or so is definitely enough to knock a person out, which is exactly what happened in that collision. That's, again, one of the reasons that football, hockey, and other collision sports now outlaw direct impacts to the head, so that whatever impact happens is spread out over the entire body over the larger mass, reducing the impact. The other way to look at this whole thing numerically is to actually go back to the concept of energy. So we talked about that in the first class, that any moving object has kinetic energy. So I'm moving here to the right. I have momentum pointing in the right direction. That's one way to describe my motion. The other way to describe my motion is to say that I have kinetic energy, and this kinetic energy depends on my mass, and depends on how fast I'm moving. The faster I move, the larger my kinetic energy. Kinetic energy scales as a square of speed. So in order to change my energy, in order to increase the energy or to decrease the energy, I have to perform mechanical work. This is something that is used in the refrigerators, for instance. This is something that your brakes do when you're trying to reduce your speed to come to a complete stop. So if you're applying and the work in physical units is the amount of force multiplied by the distance over which it's applied. So again, I can apply a force over a long distance, and that generates a large amount of work. If I apply the same amount of force over a short distance, the work is smaller, the change in the speed is smaller. So again, if you want to brake completely, you need to apply a force over a longer distance. So, like this. If I apply a force over a shorter distance, the amount of work is smaller, the change in my kinetic energy is smaller as well. So positive mechanical work increases somebody's energy, so if I keep applying force by pushing off the skates, I increase my speed. Negative work reduces the kinetic energy. That's equivalent to braking. And this work energy theorem relates the two. It says that the change in kinetic energy is always equal to the amount of work. So let me again give you a couple of numerical examples. For example, if you are jumping off some elevation, the force applied is your weight. So the ratio of your force divided by your weight expressed in kilograms is given by the acceleration. You can compute the change in kinetic energy as the amount of weight times the elevation from which you're jumping off. And that entire kinetic energy has to be eaten up by the force that's breaking your fall. So by jumping off this elevation, I first generate kinetic energy. I convert my potential energy, I'm sitting high, into kinetic by jumping. It's equivalent to me dropping the ball. At this elevation, the ball has a large potential energy. I release it, and when it hits the ground, it has speed, it has high potential, kinetic energy. Potential is converted to kinetic. In order to break that, to remove that amount of energy, I need to apply a force over some distance. So if I jump and bend my knees, I apply this force over some relatively large so-called cushion distance, which reduces the force. So if I jump from an elevation of 3 feet, and I bend my knees well, so that's 1.5 feet, I produce the acceleration of a couple of g's. That's generally okay. Your bones are designed to withstand accelerations of a few g's easily. That's one of these engineering safety margins that's built into our bones and ligaments by nature. So accelerations on bones of a couple of g's is not going to break the structure of your body. But if you lock your knees and lock your ankles, and then now the cushion distance is an inch or so, jumping up from this height is dangerous. That can produce accelerations of 40 g or so, and that's a bad idea. So again, instinctively we know this. Similar in the collisions, there was the story about, I don't know if you guys remember when you were little, there was a story about a quarterback in Detroit named Gus Frerotte. He was wearing helmets. He was wearing a helmet. Helmets have padding. This padding is not very thick. This padding is in fact designed to reduce the amount of acceleration on your head. If you're moving fast, and you're colliding with an immovable object like a wall, all of your kinetic energy suddenly is reduced by impact of the wall. If you brake over a very short distance, your head is not very elastic. So if you hit the wall with your head directly, the amount of cushioning distance is millimeters, the acceleration is large. Helmets are at least supposed to be elastic. They're supposed to squish. The padding on the inside is supposed to either break or squish, reducing the amount of force by increasing the amount of distance over which the force acts on you. But that cushioning isn't that great, isn't that thick. So this old-style hockey helmet has a cushioning of, quarter inch or so, roughly a centimeter. So if I were to accelerate like this fellow did, this fellow scored a touchdown. He was so happy. He ran into a wall and headbutted it. Didn't play the rest of the season. The guy gave himself a concussion. So, by running fast and, hitting the wall at full speed, like this, he would produce an acceleration of as much as 500 Gs. That's enough to knock out a fighter pilot, not to mention a professional football player. So, helmets, again, are in sports designed to protect you, but they will not typically save you from a very violent collision that impacts directly into the head. And that's one of the reasons, again, that the collisions to the head are no longer legal. Collisions with the head are no longer legal. The other way to describe the same kind of phenomenon is to not look at the decrease in the kinetic energy, but to look at the increase in the kinetic energy. If I want to throw something, I had a ball here somewhere. There. If I want to throw something, I can apply a force. If I apply this force over a short distance, amount of force is the same, distance is small, the ball doesn't travel very far. The amount of kinetic energy I give is relatively small. If I want the object to travel longer distance, I need to apply a larger force, and I need to wind up and really throw. In other words, I need to apply this force over a large distance, increasing the work, which will thereby increase the kinetic energy that I give to this object, like this. Nobody's asleep in the top row? Oops. Oh, my apologies. I was hoping for a larger arc. Yeah, I can throw it back. Heads up? Thanks. So in order to increase the amount of kinetic energy, you put a larger force and you generate it over large distances. I guess like this. Safer. Hockey is the same way. We can generate, where's my backpack? We can generate large forces by applying, create large kinetic energy, generate large acceleration by applying the force over longer distances and increasing the amount of force. Actually, hockey sticks are kind of interesting objects too. They in fact are tools to transfer forces, or rather transfer energy from kind of one type of mechanical motion to another. In fact, the way you're supposed to shoot, I'm told, is, hockey sticks bend. The way you're supposed to shoot is by putting your weight into the stick. Sticks bend. Bending of the stick is equivalent to storing the potential energy in the stick, similar to storing the potential energy in the elastic stretch of the string. By pulling on the weight, I apply the force over some distance, I do work. That increases the amount of energy stored in the spring. If I were to release the spring afterwards, the amount of the potential energy is transferred into kinetic energy. The more I pull over longer distance with the larger force, the larger the velocity of this object would be, similar to the motion of the pendulum. So my stick can store potential energy. I can apply full weight of my body into it by bending it over longer distance. That increases work, increases potential energy stored in the stick. That, in turn, will increase the velocity with which the spark will travel, like this. Generate large velocities, hopefully helping my team. So that's another example of generating kinetic energy by doing work, or in this particular case, by converting mechanical work first, applying the force into potential energy stored in this piece of Canadian lumber, converting it backwards into kinetic energy of the projectile. So again, this is an example of conversion of energy from one type to another through performing mechanical work. So let me pause here for just a second and see if you guys have any questions. And if not, we'll talk about gravity for just a little bit, but let me see if there are any questions for now.
So I guess I didn't understand the football players, why it wasn't an opposite force.
So the question about the football players was, why is there an opposite force? And in fact, there is. So let me see, where is my display? So if you look at, let's say this example. The two players collide. And one, this guy, Zach Follett, is applying a large force divided by its weight equivalent to the g force of 1.5 g onto another player. Third Newton's law says exactly the same force we applied backwards. Third Newton's law says for every action there's an equal and opposite reaction. So whatever force one player imparts on the other is also applied in the other direction. Of course, in this particular example, one guy is ready and one isn't. Right? The guy applying a heat is bracing for it. He's not caught off guard, and the other one is. So the actual impact on the human body can change depending on whether you're prepared for a collision or not. For example, if you're prepared to cushion yourself, you bend your knees, you bend your elbows, the impact on your body can be reduced. The other guy may not be so lucky. Same thing with the hockey collision. The guy applying a heat is ready for it. He's bracing. He will bend his knees at the point of impact. He will bend his elbow a little bit. Impact on his shoulder is a little bit smaller, and the shoulder can withstand a little bit more than a human head that's not ready for the collision. Hockey players are always told, keep your head on a swivel, right? If you watch hockey games, keep your head up. If you look for a possible collision, you have to be ready for it. Any other questions? So, but again, numerically, we can express the amount of force in the g units. And we can express it in terms of the amount of acceleration our own gravity produces. So given that it's about 3 minutes, maybe I'll stop here. We'll actually discuss gravity on Thursday. Bob Jacobson will come and tell you about ballistics, as well as satellite motion, and how gravity affects our everyday life. Thank you, guys.